Hello again, method students. This is part 2 of our sort of lesson on the expected value and the variance and the standard deviation, and we've gone through in the previous video the expected value, so make sure you've watched that one already. In this section we look at the variance and the standard deviation. So the variance, which is given by this sort of symbol sigma to the power of 2, so sigma squared. The variance of a random variable x is the measure of spread of the distribution about its mean or expected value. So essentially the variance is a measure of how spread out numbers are, and if lots of values are really tightly grouped around the mean, then you'll get a low variance, a small variance. But if the numbers are quite spread out, like lots of numbers that are well above the mean and lots of numbers that are well below the mean, then you get a higher value of the variance. So the variance is a measure of spread. And the variance of our variable x is the expected value of the squares of the deviation from the mean. The formula looks like this. The variance is equal to the expected value of x squared minus the expected value of x all squared. Now that kind of almost sounds like I said the same thing twice, like one thing minus itself. But if you look really closely at it, where that power is actually makes a difference. So each of these two things are going to be two different values, and we're going to have to find their difference. So it's the expected value of x squared minus the expected value of x all squared. The standard deviation, well, essentially, and look, we don't get too deep into what variance is and what it represents, but the variance is calculated by taking all the values, their difference from the mean, and sort of squaring them, and then finding the average of that, essentially. So the variance is determined by squaring the distance from each value to the mean, and which means it's actually taking, so for numbers like 5 above the mean, when we square it, that becomes 25 above the mean. So the variance is actually kind of exaggerating the differences between each value and the mean, and so it's no longer in the units of measurement of the original random variable. And so a measure of spread that is a more appropriate unit is actually found by taking the square root of the variance. So if we take the variance and find its square root, what we get is the standard deviation. And as you might expect, if the variance is written as sigma squared, well then the standard deviation is just written as sigma, because the standard deviation is the square root of the variance, and that's the key point. So if we know the variance, standard deviation is really easy to calculate, because we just take the variance and find the square root of it. Okay, and that's what this formula here is saying. Okay. Let's have a look at how this works in an example. So example 5 says find the variance of y given the following probability distribution. So we've got, again, this table where we've got our possible values of y, the possible values that the variable can take, 0, 1, 2, and 3, and the probability of each of those possible outcomes. So let's look at this formula and say, okay, well, the variance, right, so I'm going to write it as variance of y equals the expected value of y squared, so the expected value of y squared minus the expected value of y, right, so that's the second part, squared. Okay, so that's kind of that's like our formula really, but just using y instead of x. Right, and one of the things, this is not a compulsory way to set it out or anything like that, but one thing I'm going to actually add to the table, and I think it's useful to think about, is for this first part, when we find the expected value of y squared, well, what if we look carefully, just y squared, that's going to be taking the values that the variable can take and squaring them. So I'm actually going to add that to the table here and say, well, y squared, well, 0 squared would just be 0, 1 squared would be 1, 2 squared is 4, and 3 squared is 9. So just across the top here, it's almost like I've added a row to this table. As I said, you don't have to set it out this way, but I find it useful, particularly when you're using this for the first few times, to kind of like see what's going on with this first part, this expected value of y squared. And my next kind of tip would be to actually calculate each of these two things separately. Okay, so I'm going to, doesn't matter which one you start with, but I'm going to start with the expected value of y squared. Okay, and that will be found by taking each y squared value and multiplying by its probability. Okay, that's how we find the expected value of something. So 0 times 0.1 plus 1 times 0.3 plus 4 times 0.2 plus 9 times, oh sorry, I've marked that up, that was 4 times 0.4, sorry, plus 9 times 0.2. So you can see that the expected value of y squared is just each value of y squared multiplied by its probability, okay, which is how we normally do the expected value of something, like we're doing in the previous video. Okay, so let's work this out. So what have we got? That's going to be 0, that's going to be 0.3, that's going to be 1.6, and that's going to be 1.8. So 0.3 plus 1.6, so that's 1.9 plus 1.8. So if I've done that right in my head, I think we're going to get 3.7. The expected value of Right, so that's our expected value of y squared. Okay, that's that first part. Now we're going to work out the second part, the expected value of y, and then square it. So let's just get the expected value of y. So we're kind of doing this step by step, and then we'll put each bit back into the formula. The expected value of y is just each y value multiplied by its probability, and we sum them together. So that's 0 times 0.1 plus 1 times 0.3 plus 2 times 0.4 plus 3 times 0.2. And when we work that out, that's going to give us what, 0.3, 0.8, so I'm up to 1.1, plus 0.6, so I think we're up to 1.7. Okay, so we've kind of got the two bits that we need here. We can go back to this formula and say, well, the variance of y will equal the expected value of y squared, and that's 3.7, minus the expected value of y, which is 1.7, squared. Right, so these two values are going to give me the variance of y. I should have grabbed a calculator because I'm not going to be able to do that very well in my head, I don't think. Bear with me 2 seconds, I'm just reaching over my calculator. Clearly not very well prepared. Doing it on the phone as well, that doesn't help. So 1.7, I should have been able to work that out actually. 3.7 minus 2.89. And so the variance is 0.81. The variance of y is 0.81. Okay, so that's just a little bit of practice at applying that formula. And you can see a good way to sort of work it out is to start with the formula, but work out each part separately. Otherwise your working gets a bit messy, and then put them together and do the final calculation. Okay, a bit like with the expected value, with the mean, there's also sort of like a variance theorem, this sort of additional rule that can be applied. This is saying the variance of a times x plus b will equal a squared times the variance of x. Now, again, that's kind of a complicated thing just to look at, but if we think about this in the context of just like a simple example with numbers. So I want to go back to, I think the numbers I wrote out in the last video were 8, 10, and 12. Let's just imagine that was our entire distribution, right? Now, if we think about this, the variance is a measure of how far above and below each number is from the mean. So basically the variance would be calculated by saying, well, the mean of these numbers would equal 10. So this first number is 2 below the mean, this middle number is equal to the mean, and this third number is 2 above the mean. So the variance would be calculated by squaring these numbers, right, and then finding the average of those. Essentially that's what the variance does. So it's a measure of like how spread out the numbers are, or at least on average how spread out the numbers are from the mean. Now, if we were to, let's just say we were going to add 1. Actually, no, add 5. I'm going to add 5 to each of those numbers, right? So I'm going to take the entire distribution and do the variable plus 5. Well, that'll give me what, 13, 15, 17. But that's had no impact on the spread of the numbers, right? The mean of these numbers would now be 15. But how spread out they are, how far away each of them are from the mean, has not changed at all. So that's why when we look at this sort of theorem up the top here, even though there's that plus b at the end, that hasn't really been included on the right-hand side because that plus b has had no bearing on the variance. It's not changed how spread out the values are, okay? However, if we were to take those three numbers and multiply them by a value, let's just say multiply them by 3, well, that is going to influence how spread out they are from the mean. If I multiply them by 3, well, 8 3s are 24, 10 3s are 30, 12 3s are 36, right? So the mean has now become 30. This number's 6 below the mean, this number's still equal to the mean, this number's 6 above the mean. You can see that the variance is going to have changed because these numbers are now more spread out because we've multiplied them by 3. And since the variance works by squaring these differences, then the amount that the variance, or the factor that the variance has changed by, is actually 3 squared, okay? And more generally speaking, if you multiply your variable by a, then the variance is going to increase by a factor of a squared, okay? That's where this theorem kind of comes from. Ultimately, it's one of those things where if we know what the rule is though, we can just apply it, right? So it's good to try to understand it, obviously, but even if you don't, even if that didn't make much sense, you'll see a sort of pretty straightforward application of it in this next example. So this one we've got, given that the variance of x is 4.5, find the variance of 3x plus 2. Okay, well the variance of 3x plus 2, we said that the plus 2 is not really going to have any bearing on the original variance, okay? But what's going to happen with this 3 is it'll become our factor in front squared times the original variance of x, and as we said, this plus 2 doesn't change the variance, so it doesn't kind of have any influence in our calculation. So we get 3 squared times 4.5 because that was the variance of x. So 9 times 4.5, and what's that, 9 4s are 36, half of 9 is 4.5, so 40.5 would be the new variance. All right, example 7, back to a worded problem here. So in order to encourage carpooling, a new toll is to be introduced on the East Gate Bridge. Oh, it almost sounds like something that exists. If the car has no passengers, a toll of $2 applies. Cars with one passenger pay a $1.50 toll. Cars with two passengers pay a $1 toll, and cars with three or more pay no toll. Long-term statistics show that the number of passengers, which we're calling X, follows the probability distribution given below. Okay, so we've got our possible values, our possible outcomes for X, their associated probabilities, and in this row here we can kind of add the toll paid. So it said, well, if there's no passengers, the toll is $2. If there's one passenger, it's $1.50. Two passengers was $1, and three or more pay no toll. So there'd be zero toll if you've got three or more passengers. I don't know why I do things like call it the East Gate Bridge. I'm sure that no one's going to sue me if I called it the West Gate Bridge or the East Link or anything, but I don't know. I don't know why I make it that way, but that's what I do. So apologies. Okay, complete the toll paid row of the table above. Oh, I already did that. Okay, part 2, find the expected toll to be paid per car. So we're trying to find the expected value of the toll, and that's really important, okay? So we're actually finding the expected value of the toll. So I'm actually write it like E toll, because we didn't give that a letter, okay? But it's not the expected value of X, right? That's important. The expected toll would be, okay, the value itself multiplied by its probability, the sum of the value of the toll times its probability. So it'd be 2 times 0.4 plus 1.5 times the probability of that happening, which is 0.35, plus 1 times 0.2 plus 0 times 0.05. Not that that last one's going to matter. So it's just the expected value of the toll is each possible value of the toll multiplied by its probability, and we sum them all together. Okay. So what have we got here? I'm going to check this in the calculator because I'm feeling lazy. So 2 times 0.4 is 0.8. 1.5 times 0.35. Yep, plus 0.8. So up to 1.325, plus another 0.2 gives me 1.525. Okay. And find the standard deviation of the tolls paid. Well, the standard deviation of the tolls paid. Okay, so we're going to have to work out the variance first and then square root that to get the standard deviation. So let's start with variance of toll. And remember that equals the expected value of the variable squared, like that, minus the expected value of the variable all squared. Okay, so we've actually got the 1.525 to put in this second part. What we don't know yet is the expected value of the toll squared. So what we're going to do is it's the expected value of the square of each of these numbers. So I'm going to write it like this. So actually I won't do equals, I'll do separate working here because I think that's a better way to set it out. Expected value of toll squared equals, so we take the toll, which is 2, we square it, and then we multiply that by its probability. Okay, plus 1.5, so the value of the next value of the toll squared, because it's the expected value of the toll squared, multiplied by that probability, and so on, plus the next value of the toll squared times by 0.2. And even though it's not really necessary, I'm going to write at the end here, plus this value of the toll, so 0 squared times its probability, 0.05, even though we know that term's going to become 0. All right, so we're going to sort of add all that up and work that out. Again, I'm going to go calculator here. I should have been better prepared and brought my proper calculator over. I'm going to try to wing it and see how this goes. Plus 0.2 equals, and then what's this going to be for? It's going to be plus 1.6. All right, so if I haven't marked that up, we're going to get 2.5875 as the expected value of the toll squared. Okay, so now we've got the two bits that we need for our variance, so we can go back to this and say, well, the variance of the toll will equal this value here, 2.5875 minus the expected value of the toll squared, so 1.525 squared. Okay, that answer will give us the variance, so 0.525 apologies for this, I should have worked these answers out in advance, or brought my proper calculator so I could do this a bit quicker. 0.2611875. And I also should have made this question rounded to a certain number of decimal places, because at this next step we're going to get a silly number of decimal places here. So remember that the question was asking for the standard deviation of the tolls paid, so you can write it like this: SD of toll just equals the square root of the variance of the toll. So this is actually the easiest step. We're just going to take the square root of that value there. and that will be our standard deviation. And we know in a lot of questions where it doesn't tell you to round, that means give an exact value. This one is just an error on my part. It should have said to round to a certain number of decimal places. And I've got to tilt my phone sideways because it doesn't even give me the square root button. All right, so we're getting 0.5117, and let's just go to 4 decimal places. Okay.